So to open today's program, I'd like to first say how grateful I am for the opportunity to continue to live and learn and teach on the traditional territory of the Musqueam, Squamish, and Tsleil-Waututh people. Since time immemorial, they have been incorporating the practice of observation and storytelling into science and everything that they do. And we are always so grateful to have the opportunity to learn from them and incorporate that in our practice, both within OceanWise research and education in all of our programs and initiatives. So we welcome everyone, and without further ado, I'd like to turn it over to Dr. Marie Noel, and I'll hand over the screen sharing ability in just a moment for you there too.
All right. Well, good afternoon, everyone, and thanks for joining us. My name is Marie, and I manage the Ocean Pollution Research Program at OceanWise. And today I'm just going to give you a little bit of information about what we're doing in terms of research on pollution in the marine environment at OceanWise, with focusing on contaminants in marine mammals. So first, an overview of our program. So there's two main components. So the first one is our pollution tracker program, which is a marine pollution monitoring program. And we launched it in 2015. And it's the first coast-wide marine pollution monitoring program in BC and in Canada. So in 2015, we've collected over 50 samples along the BC coast, so all the way from Haida Gwaii to the Lower Mainland and around Vancouver Island. And we focus on two types of samples. So that's the two pictures that you can see here at the bottom of the screen. So we look at sediment and we look at mussels. So why do we focus on those two? Well, they are what we call the gold standard when it comes to contaminant monitoring, because sediment can act as a sink and a source for contaminants in the marine environment. And mussels, well, they filter a lot of water, and they don't move. So they're going to be able to give us an indication of the local state of the marine environment. So in those two types of sample, we've monitored over 400 individual contaminants. And this program is highly partner supported. So we get funding from the government, from port authorities, from industries, from First Nation. And the goal is really to identify pollution priorities, but also identify where the contaminants are coming from, with the ultimate goal of informing on best practices to be able to reduce ultimately the levels of contaminants in the marine environment. And we have a great website, so pollutiontracker.org, that you guys can go check out, where we share with the public all the results that we have from this monitoring program. So I just took a few screenshots of what you can find when you go to this website. So you would get to like a landing page, and then you would have access to different types of information. So here in the middle, you can see that we provide you with information on different types of contaminants that we look at, what they are used in, if they are still in use or if they've been banned. Then you would have access to an interactive maps. So all those little green dots will show you where we've collected samples. And then you can click on each individual dot, and that would give you information of contaminant levels. So I picked here as an example one of the sites that we had in Victoria Harbour. And what you can see is that we have ranked the sites. So here, Victoria Harbour sample number 3 was like had the second highest level of contaminants overall along the BC coast. So we did find that Victoria Harbour was a hotspot for contaminants during this first phase of pollution tracker. And so I really encourage you to just go check out this website so you can get a little bit more information about the different types of contaminants, but also where you find them along the coast. The second component of our program is the marine mammal toxicology program. And the goal is to investigate contaminant levels and their related health effects in marine mammals. So here along the coast of British Columbia, we look at killer whales, we look at harbor seals, but we also do some work in the Arctic. So we look at beluga whales in the Western Arctic and ring seal in the Eastern Arctic. But for today, I'm going to focus on what's going on here in BC, so killer whales and harbor seal work. So as most of you know, probably the British Columbia coast is one of the most productive and diverse marine environment in the world. So we have a lot of iconic marine species that depend on this marine environment. I put here a little bit of a few pictures as examples. So we have the iconic killer whales, we have harbor seals, Chinook salmon, bald eagles, but there are also a lot of people living along our coast, especially in the lower mainland. So here is just like a high-level map that can give you an indication of the different potential sources of contaminants that you can have in the lower mainland and also Washington State. So as an example, we have oil refineries, agriculture, municipal effluents, and also urban effluents. And all those contaminants from these different sources can end up in the marine environment and have the potential to affect the marine organisms. So when we talk about marine mammals here along the BC coast, obviously we think about killer whales. And I don't know, maybe some of you have joined some of the past webinars that we had in the past couple of weeks. So you might have heard some talks about killer whales already. But just as a reminder, we have 4 populations of killer whales along our coast. So we have the northern resident here. So, sorry. It's the first map on the left. And you can see that their range is all along the BC coast. And then we have the southern resident, which is the second map. You can see their range in green. So the residents are fish eater. And so we have some critical habitats that have been established by the government, which are the yellow areas that you can see in the first 2 maps, which are usually areas that are really important for the whales because they spend a lot of time feeding or foraging in the area. Then we have the transient killer whales. So those are the marine mammal eater. There are about 400 transient along the BC coast. And as you can see, they roam around the whole coast as well. The last population is a population of offshore killer whales. A little less is known about those whales. We know that there's approximately 300 individuals, and they have a more of a diverse diet. So they reported to eat shark, salmon, and also halibut. And these species of whales have been listed under the Species at Risk Act. So 3 of those are listed as threatened. So you have the northern resident, the transient, and the offshore. And the southern resident have been listed as endangered. Because as of the end of December 2019, there was only 73 individuals remaining. 3 main threats have been identified that prevent the recovery of those populations of killer whales, and especially the southern residents. The first one is limited food. So as I mentioned, the residents are highly specialized. So they are focused on salmon and especially Chinook salmon. So the decline in salmon is impeding the recovery of this population. The second threat is noise and disturbance. With all the boats on the water creating background noise, which would prevent them from communicating with each other, but also finding their prey. And the last threat is contaminants, of course, which is what we're going to focus on today. So I want to talk to you guys about 2 types of contaminants. You don't need to worry about the crazy name, really. Let's just focus on the acronyms. So the first one is PCBs. So they were used in electrical equipment as cooling fluids, and they were widely used across the world, but also in North America between 1929 and 1977. So they were banned over 30 years ago, but we're still interested in them because they're really persistent. So we can still find them in the marine environment at concentration that are concerned for marine organisms. The second one I'm going to talk about is PBDEs. So those are flame retardants. They are used in furniture, plastics, paints, textile, electronics to prevent fire. And they have a little bit of a different history. So they were heavily used in the 80s and the 90s, and then banned in the early 2000s. So I will get back to those, and I'm going to talk to you about those two types of chemical along throughout the presentation. So why, you might wonder, why do we care about contaminants that are found in like your computer or your couch, and what does this have to do with marine mammals? Well, you have different sources of contaminants to the marine environment, as you saw in that first map. So you can have point sources with urban effluents, or you can have from like industrial activities. And it's also important to know that these contaminants can move in the marine environment. So for example, once they get released, they can move with the ocean currents as well as throughout the atmosphere. So for example, in the Arctic, we might think about this environment as pristine, but we do find these chemicals up in the Arctic because they have been transported from southern locations to the Arctic via the ocean and via the atmosphere as well. So once they get transported, they can be deposited with the rain or with the snow onto the marine environment. And then they can be taken up by the food web. So if we look at a little bit at the food web, so as I said, those chemicals, here's a diagram that takes PCBs as an example. So they are deposited into the marine environment, coming from urban sources or from the atmosphere. But what's important to know is once they enter the marine environment, they're not going to stay floating around in the water. They're going to stick to different particles. So they're going to stick to sediment, for example, and then sink into the bottom of the ocean, or they're going to stick to phytoplankton, which are little algae. And those little algae are going to be eaten by zooplanktons, which are little invertebrates, which will in turn be eaten by different species of fish. So here in the killer whale food web, that would be eaten by herring, then by salmon, to end up then in killer whales. And once those chemicals enter marine organisms, they're going to stick to their fat, which means it's going to be really hard for the animals to get rid of those chemicals. So the concentrations are going to increase at each level of the food web. And then you usually end up with really high concentration at the top of the food chain, so in killer whales or harbor seals or other marine mammals. So 3 main reasons why you usually have high levels of PCBs and PBDs in marine mammals. As I just mentioned, and we see in this diagram, they are at the top of the food chain. Also, they are very long. Those chemicals are going to accumulate throughout the life of marine mammals. So a very old marine mammal is going to have concentrations that are significantly higher than a young animal, for example. And they accumulate contaminant in a thick blubber layer. As I said, contaminants, they love the fat. They're going to stick to the fat. And marine mammals, they have a really thick blubber layer that allows them to be insulated and stay warm. So here on this picture, it's an example of like a blubber sample that was taken from a harbor seal that was dead. And so just to give you an idea, like the thickness of the blubber layer can vary anywhere from like a couple centimeter in smaller marine mammal species to 40 or 50 centimeter in the big whale species. So at the Ocean Pollution Program, we study killer whales. We look at contaminant levels and we look at their health. So here are a couple of pictures from the field. So as I said, because contaminants accumulate in the fat, we usually collect a tiny little piece of blubber via a biopsy dart that you can see here on the top left picture. So it really takes like a little tiny piece of blubber, which is about like the size of an eraser, maybe just a little bit taller. And then the samples are being preserved in liquid nitrogen, so really, really cold, so we can preserve those contaminants. And then once we're back in the lab, we can extract them and measure them as well. So while we do contaminants on killer whales, as I mentioned, the southern residents are endangered. So we haven't collected any samples from them in the past few years because we want to help them recover as much as possible, so limit the stress in the population. So we do not collect samples from this population anymore. And we use other animals as proxy to look at killer whale health. So that's where herbaceals are very useful because they live in the same environment as killer whales, so they are exposed to this similar level of contaminant levels. They are easier to study, obviously, because it's way easier to get a sample from a herbaceal than a killer whale. And we consider them our marine lab rats because there have been a lot of studies done over the years and we know a lot about their biology and physiology. So it can really help when you're trying to figure out the health effects that these contaminants have on marine mammals to have a good understanding on the biology of these animals. And there is a lot of herbaceals along the coast here. In BC, we have about like 100,000 individuals all along the coast. So that allows us to look at areas that are a bit more contaminated, so here down in the lower mainland, but also areas that are more pristine, like on the upper coast. So on this diagram, it gives you an idea of like different samples can provide different types of information. And also different types of animals can provide you different types of sample. So at the top here, you have the killer whales, and there have been other researchers looking at samples of blood, feces, to look at hormones as well and the health. Obviously, you have the skin and blubber biopsies that we do collect, and those are common between killer whales and herbaceals, so we can obtain lots of samples in the two species. But obviously, when we catch a herbaceal, we also have access to other types of samples. We can take a blood sample, for example, or we can look at whiskers and fur, because that can give us an indication of mercury levels, because that's where mercury is going to accumulate. But for today, we're going to focus on the blubber to look at contaminants and health effects. So how does it work in the field when we want to collect samples from herbaceals? So usually we focus our collection on herbaceal pups. And there are a few reasons for that. First of all, they're easier to catch. But also when we want to be able to compare between different sites, I mentioned that marine mammals accumulate contaminants over their whole lifetime. So if you catch herbaceals of different age, then it makes it hard to be able to compare between different sites, because if at one site you're collecting really old herbaceal and at one site you're collecting younger herbaceal, obviously you're going to have a different in concentration, but it's going to be due to age and not necessarily due to the local contamination. So by collecting pups of similar age, we're able to reliably compare concentrations over space, but also over time as well. So usually how it works, herbaceals, they haul out here in BC, usually on rocky shores, but also on log booms. So here you can see a mother pup pair on the upper left. And usually we call it boat rush. So usually we go towards the haul out site with the boat, jump off the boat, and then catch the herbaceal pup with a salmon landing net. And then we come back to the main research boat, and then we're going to collect a wide variety of information. So here you can see the bottom left picture is how we weigh a herbaceal. So those pups are between 4 and 6 weeks old, and usually they weigh between 20 and 25 kilo. We look at their teeth. It gives us an indication of their age a little bit more precisely and also overall health. We collect a blubber biopsy on the top right picture here. We collect whiskers. And then finally, when we're all done, we just release the little pup back in the water, close to where it was caught. This whole process takes about 15 to 20 minutes. We try to do it as fast as possible to limit the stress on the animal. And when we release the herbaceous pup, we usually witness that it is reunited with its mom within a couple minutes. So what kind of information can we get from those samples? So this is a map from a paper that we published a few years ago. So you can see those are PCB levels. So remember those chemicals that were banned in the 1970s, measured in herbaceous pups from different sites. So all the way from Queen Charlotte Strait, Strait of Georgia, some in Vancouver, and some all the way down in Puget Sound, so in the Seattle area. And you can see that the levels in the pups collected in the Seattle area are significantly higher than the other sites. So this types of study allows us to identify what we call contaminant hotspots, so areas where you have high levels of contaminants. And in this case, for PCBs, it would be Puget Sound. So that would be related to the industrial activities that are happening around, especially with the city of Seattle, but also with the geography of the area. So Puget Sound is this basin that there is a high residency of the water. There's not really much exchange with the open ocean. So contaminants tend to be trapped in this specific basin. Another type of information that we can look at is temporal trends. So these herbaceous pups have been collected on a regular basis for a number of years. So since we have data since the early 1980s, and that's really useful because that allows us to see the trends in the marine environment. So I put that on the left here, you have the PCBs here, and I put the red line to remind you that they were banned in the late 1970s. And you can see that the concentrations have been decreasing since then. The PBDEs here on the right, slightly different story. So again, the red line is showing you the time where they were banned. So before the ban, you can see that the concentrations in herbaceous pups were increasing very fast in herbaceous. And then after the regulations were put into place, obviously there is a little bit of a lag in the response of the marine environment, but you can see that since then we have had concentrations that have been decreasing. So the marine environment is responding to regulations being put into place, which is a good news story when you look at contaminants in the marine environment. So just a few conclusions and a few things to recap. There are high levels of toxic chemicals that are found in marine mammals, so such as killer whales and harbor The chemicals of concern that I've talked about today, so PCBs and PBDEs, even though they were banned in the case of PCB more than 30 years ago, they are very persistent in the marine environment. So we still find them in marine mammals today. Killer whales along our coast, unfortunately, are one of the most PCB contaminated marine mammals in the world. We do have a bit of a good news story in the sense that we do see a decline in levels in harbor seals after the regulations were put into place. However, it's important to note that the levels, today's level, are still high enough to cause adverse health effects. And obviously, I didn't have time today to go into much detail in terms of health effects. But there have been a lot of studies locally in harbor seals and killer whales, but also in other marine mammals around the world, looking at PCBs and PBDs impacts on their health. And there's like three main target really. They can impact the immune system, which means the individuals will be more sensitive to diseases. They can also impact the reproductive system, and impact also the endocrine system, which is impacting the levels of hormones that animals have in their body. So it's really important to keep monitoring levels of contaminants in the marine environment so we can keep on top of what's going on, and also look at other types of contaminants, which is what our pollution tracker program is for. Like, we look at this wide array of contaminants so we are able to identify what we call emerging contaminants in the marine environment. So that's all I have for today. I'm happy to take questions, but if you want more information, I've put three links here. So pollutiontracker.org that we talked about. There's also oceanwatch.ca. So our Ocean Watch group here at OceanWise has been publishing those reports on the state of the marine environment, and there's one on the BC coast, and you can find a couple articles on contaminants in the marine environment and in marine mammals especially. So if you go to oceanwatch.ca, you can type in the one for marine mammals, and then feel free to send me an email if you have additional questions.
Wonderful. Thank you so much for such a fantastic presentation, Marie. And we have lots of questions coming into the chat. And a big kind of curiosity from our audience is, with PCBs being banned, as you said, around 30 years ago, what makes them so persistent in the sediment, or why do we see so much of them still?
Yeah, so they're, without getting into too much detail, basically it's their chemical structure makes it that it's very hard for them to be broken down by anything. So they're going to have a really long residency time in sediment, and also animals are not really able to metabolize them. Usually if you take other types of contaminants, some of them, the animals are going to ingest them, and then they have a variety of enzymes in their liver that are able to break down different types of chemicals. It's the same for humans. Like, let's say if you take medication, then your liver is going to break down this medication so your body can then eliminate it. But for PCBs, just because the way their structure is, it's just very hard for any organism to be able to break it down. And that's why PCBs and PBDEs, and I didn't, I don't know if I can go back. I had put this little, I didn't want to go into too much detail about the chemical structure, but you can see, so they're both very persistent, and you can see they have a similar structure with those two rings here. They both have two rings. It has to do with the chemical structure that makes it very hard to break down.
Wonderful, and I guess this is a great slide to ask this next question, so what we're finding in terms of PCBs and PBDEs in the environment, did they kind of stop entering the environment when they were banned, or are there still, pieces of furniture or different products that are making its way into the oceans, creating this problem?
Yeah, that's a good question. Because obviously when chemicals are banned, it's usually they ban the production, and then they ban the manufacture of products containing those chemicals. But obviously if you've bought products, let's take PBDEs, for example, if you've bought products before it was banned, 2003, 2004 in Canada, they would still contain those PBDEs. So obviously you still have a constant, not as high, but you still have potential sources for those chemicals to enter the marine environment. That's why it's important, especially in the case of PBDEs, because you're most likely to have those in your house as opposed to PCBs that were more on the industrial side of things. But if you have pieces of electronic equipment, it's important to dispose and recycle of it in the proper way to make sure that you don't have those chemicals that end up in the marine environment.
That's a great action item for our audience. I know we've had several questions of kind of what can we do after today's presentation to try and help and reduce how much these chemicals are getting into the environment. So I think really, being careful about how you dispose of things in your house, whether you're doing a renovation or it's an older piece of furniture or something that you might have, to kind of do your homework and try to make sure that you're disposing of it in a proper way and recycling it if you can.
Yeah, and there's also, like we've talked about those two particular type of contaminants, but there's also, as you said, do your homework when you're looking at even at cleaning products for your house or pesticides that you might want to put in your garden because, I don't know, the slugs are driving you crazy or something. You need to think about all those things because ultimately a big part of it would end up in the marine environment.
Wonderful. One question that came in about the research on the harbor seals with by using pups, are they still drinking milk at that point, and are they getting any of those contaminants from their moms, or are they already starting to fish for themselves?
Yeah, so 4 to 6 weeks old. So it's usually around the time that they get weaned. But obviously the mom is going to transfer contaminants when the pup is still in utero, so before birth. And then she's going to transfer some contaminants, yes, you're right, like through the milk as well. So the pups are usually on the edge. So it depends. That's why we're trying to assess as well. That's why we look at the teeth. And then we look also, we look at the umbilical cord. That gives us like a little bit more of a more precise idea of the age of the pup. So that gives us an indication if it's still nursing or not. And when we do, we take a blood sample and we can also look how fatty the blood was, which gives us an indication if the pup had just been feeding or not. So usually it's just mostly from the mom. They might, if some are a little bit further along, they might have started being totally weaned, but usually they're just getting weaned.
Wonderful, thank you. And then looking a little closer, thanks for sharing the link to the pollution tracker website. And with all of that data, is the government or how is the government using some of that data?
Yeah, so we're part of, so there are different types of information that we can provide and expertise that we can provide to the government. And we are part of several groups, like including a technical working group for the recovery of killer whales, for example, where we share all this data as well that can help us identify the levels of contaminants in killer whale critical habitat, for example. And we are also being able to inform on, so the government has a set of what we call environmental quality guidelines, which sets guideline for how the levels of how low the levels of contaminants needs to be in the sediment in order to be safe for the food web. So all this data is being shared and we're able to advise as well on the development or update of some of the environmental quality guidelines.
Excellent. That's always good news too, to hear how it's being used and kind of activated in that way. A couple of questions that are also coming in, and I think it was one of your slides looking at kind of the various PCB levels in different areas, is kind of how come they seem to vary so much in a small area? Do we know why some areas are higher than others?
Yeah, so I'm guessing that's with the slide, like with the map. So those pups were captured really like in the south side of like Puget Sound. So obviously it's a very industrial area with the city of Seattle. And as I said, the geography of this basin makes it that contaminants tend to be trapped even more in this environment because there's not much exchange or flush out with the open ocean. So that's one of the factors that makes it that contaminants are higher in this specific environment.
And this might be a more seal specific question, but does focusing on pups also help with getting less variation in how far a harbor seal could even travel to get its food?
Yeah, actually, that's a good question. So actually, one of the reasons as well that we use harbor seal is that they're fairly what we call local animal, I guess, for a marine mammal. So they're usually going to stay within like 30 kilometers square of their main like haul out. So some might venture further away, but like so we consider that they give us like a local signal of contamination just because like if we take killer whales for example, like they're going to travel long distances up and down the coast, whereas harbor seal they tend to stand fairly local. So yes, that's also one of the reasons why we look at them when we look at spatial variation of contaminants.
Awesome. And I think we do have a couple more minutes, maybe for one or two more questions. So if anyone in our audience has one that they'd like to put in the chat or in the Q&A for us, we're getting a couple more questions kind of about how these contaminants move up the food chain. So if they are in the sediment or at the bottom, I know you said there was kind of less, flow through and flushing out of those areas. But kind of how are they making their way from these tiny phytoplankton into some of these larger species?
Yeah, so I put up, and I don't know, do people see the slides still or no? Okay. So I put up the graph again. So when they are, and we can look at yeah. So when they enter the marine environment, and once again, it has to do with their chemical properties. Those chemicals do not like to stay in water. It's kind of like when you put oil in water, like they don't mix with each other. So it's the same idea as like they want to get out of the water, so they're going to stick to whatever they can. So sediment, for example, is one thing. So that's why I said that sediment can be a sink for those contaminants because they stick to the sediment. The sediment is going to fall at the bottom of the ocean and it's going to be stored there. Or they're going to stick to other particles that are floating around in the ocean, just like algae. And algae are really the bottom of the food web. So then when you have zooplankton that's going to eat those algae, that's the first chain of how contaminants enter the food web at the very bottom, when those little algae are being eaten by little invertebrates. And then because animals can't break them down, it's going to stay in their body. So once the prey, so let's just say a herring here, for example, is eating the zooplankton, is going to eat the PCBs at the same time. And once again, it just can't break them down. It's going to stick to their fat. So then the salmon is going to eat the herring with the PCBs and so on. So then and because the amount of food that is being consumed as you go up the food chain is bigger and bigger, then you have more and more contaminants that are making their way all the way up the food chain.
Excellent. It's always good to take a moment and think about how everything is connected that
Yes.
way. And I know we're almost done on time. So again, I encourage our audience, if you do have any last questions that you'd like to send our way. It's so wonderful learning about this ongoing work that's really happening kind of in our ocean backyard so locally. And I personally love seeing, these presentations each week, is seeing all of those connections. So just last week we had Eric talking about the importance of algae in the food chain. And so you can always go back and check out some of those past programs. I just put the link in the chat for you as we're posting the recordings as we go each week. And so we do have another couple of questions coming in here just before we wrap up for today. And so one is talking a little bit or asking about coral, and that if they are growing maybe off of a ship or something that has been sunk in the ocean, could this be a new source of contaminants in the water? Or do we have to watch out for some of these kind of sunken wreck? So that might.
I'm not entirely familiar with the specific of like a ship that you sink in the ocean to make habitat, but I know that everything that needs to enter the marine environment, there are regulations and it is tested to make sure that the levels are safe for marine organism. So I would assume that similar testing is done when that type of work is being done, but I would have to get back to you on that one.
Definitely. And so kind of follow-up question from the audience was if these PCBs, let's say, that have been banned for the past 30 years, obviously they're not being not entering the environment at quite as rapid a rate. Can they kind of be stirred up from those sediments and re-released? And that's maybe somehow of how the algae and phytoplankton are getting it in their systems.
Yeah, and it's back to your comment earlier as well, saying that some older equipment that might still contain PCBs might still be a little source of PCBs today to the marine environment. And yes, also sediment are a sink for contaminants, but also I said a source for contaminant, because if you have disturbance in the sediment, then it puts whatever is in there in suspension into again.
Wonderful. Well, thank you so much. The audience is sending lots of great messages that they learned so much, and I did as well. And we really appreciate your time and your presentation. And so again, to everyone watching, this recording will be up in the next little bit on our YouTube channel at OceanWise, as well as on our education.ocean.org website for you to find. And if you'd like to dig a little deeper, and those were some great links shared, as well as Marie's email if you do have any questions, and we always love to hear from you. And so thank you so much. I'm going to see if I can just nab back the presentation ability here so I can show our last slide. And it's so great to have such positive feedback from our audience, seeing that all coming in today. We're really excited, I guess, more on the theme of what we can do to help out our environment and take action. Next week's Tales from the Deep program is going to be with Shoreline Cleanups Julia Wakeling, and she's going to be talking about scientists on the shoreline and learning about how we use that data to inform our decisions while we're doing shoreline cleanups, as shoreline cleanup has just kind of reopened to small group, household, and solo cleanup so that people can get back out on our shorelines and cleaning up and helping kind of assess what is out there, what do we need to focus on in terms of what we're seeing on our beaches. And as always, we'd love to have you all stay in touch and stay connected with us, so you can find those past recordings, including this one, shortly on our education.ocean.org website. You can find out upcoming programs at ocean.org/learn online, or follow our posts on Twitter at OceanWiseEDU, as well as OceanWise Research on Instagram. And new this week, maybe some of you saw it already, but we now do have a Facebook event that you can follow to get all the latest updates and announcements of our Tales from the Deep program. So if you go to Facebook and follow Oceanwise and events, you'll see Tales from the Deep listed there to show you what's coming up next. We are so excited that we're already several weeks into the reopening of the Vancouver Aquarium, but as always, things are going kind of week to week, month to month, and we really appreciate all the community support we've seen and the kind of ask to continue looking to how you can support, whether it's sharing these programs, sharing the word with others, or making a donation if you can, is always appreciated. And you can find out more ways to connect to some of those community initiatives by checking out vanaqua.com/saveva/community. And so thank you again, everyone. It was wonderful to have you with us on this July afternoon, and we look forward to seeing you next time. So take care, everybody, and thank you again, Marie.
Thanks, everyone.